December 5th, 1941, 6 miles west of Moscow. Temperature -38 degrees Fahrenheit. Obergefreiter Klaus Becker crouches beside his Panzer III, breath freezing into ice crystals before it leaves his mouth. He's been trying to start the engine for 40 minutes. The starter motor whines, grinds, stops. The battery is dying. The oil in the crankcase has turned to something resembling tar. Around him, scattered across the snow-covered field, sit 23 more Panzers from his unit. Silent, dead, frozen solid. These aren't combat losses. Not a single Soviet shell has hit them. They've been killed by the cold. 300 yards east, across the same frozen field, a Soviet T-34 rumbles to life on the first try. Its engine clatters, rough but running. It begins moving forward through the snow, toward the immobile German tanks. Becker watches it approach, his hands too numb to hold his rifle properly. He's wondering how a Soviet tank, supposedly inferior, supposedly crude, can start in this murderous cold while his sophisticated German machine sits frozen and helpless. The answer isn't tactics or courage or training, it's lubricant. Specifically, it's the difference between oil that turns to sludge at -40 degrees Fahrenheit and oil that keeps flowing. It's the difference between engines that run and engines that don't. And it's one of the least discussed but most crucial factors in why Germany lost the Eastern Front. This is a story of how American petroleum engineering, refined through decades of harsh civilian winters from Montana to Minnesota, gave the Soviets a critical advantage in the deadliest winter warfare in human history. How the science of keeping engines running in extreme cold became as important as armor thickness or gun caliber, and how something as mundane as motor oil helped determine the fate of nations. Let me explain what -40 degrees Fahrenheit does to an engine, because until you understand this, nothing else makes sense. Motor oil at room temperature flows easily. Pour it from a bottle and it streams smoothly. This flowability, called viscosity in engineering terms, is what allows oil to do its job. It needs to flow through tiny passages, coat moving parts, create a thin film between metal surfaces that are sliding against each other thousands of times per minute. As temperature drops, oil molecules slow down and stick together more. The oil thickens. At 0 degrees Fahrenheit, most conventional oils from the 1940s had roughly doubled in viscosity compared to their 70 degree Fahrenheit performance. At -20 degrees Fahrenheit, they'd quadrupled. At -40 degrees Fahrenheit, many oils essentially became semi-solid, still technically liquid, but so thick they wouldn't flow through an engine's lubrication system. Here's what that means for starting an engine in extreme cold. When you hit the starter, you're trying to spin the crankshaft, which has to turn pistons inside cylinders, drive camshafts, spin oil pumps, and overcome the resistance of oil that's turned to cold molasses. In summer, with thin oil, the engine spins freely. In deep winter, with thick oil, the starter motor is trying to turn an engine that feels like it's filled with honey. The electrical system compounds the problem. Lead-acid batteries lose capacity in cold. At -40 degrees Fahrenheit, a battery delivers only about 40% of its rated power. So you have 40% of normal battery power trying to spin an engine with 400% of normal resistance. The mathematics don't work. The starter grinds, slows, stops. Even if you manage to start the engine, say by heating it externally or using a direct fuel injection primer, running on thick oil damages everything. The oil pump can't move the sluggish oil through the system. Bearings run dry. The thick oil creates so much internal resistance that it absorbs engine power. Your engine is fighting itself just to run. German forces discovered this horror in December 1941 as temperatures plummeted and their equipment began failing en masse. The German military had prepared for winter, but not for a Russian winter. German planning assumed temperatures similar to what they experienced in Germany. Cold, yes, but rarely below 0 degrees Fahrenheit. They'd issued winter clothing, antifreeze for radiators, and cold weather starting procedures. What they hadn't fully grasped was that Russian winter meant -20 degrees Fahrenheit was normal, -30 degrees Fahrenheit was common, and -40 degrees Fahrenheit was possible. In these temperatures, their standard military oils, perfectly adequate for European winters, failed catastrophically. Heinz Werner Schmidt, a German officer with the 18th Panzer Division, wrote in his diary on December 8, 1941, morning temperature -42 degrees Celsius, -44 degrees Fahrenheit, ordered to advance at 0600. By 0800, only 4 of our 26 Panzers are running. The rest won't start. The mechanics say the oil has frozen. One crew tried starting their engine for so long they burned out the starter motor and drained the batteries completely. The tank is now completely dead. Not even the radios work. This wasn't isolated. Across the entire German front line outside Moscow in early December 1941, tank readiness rates dropped below 50% in some units, with cold-related failures outnumbering combat damage. Trucks wouldn't start, half-tracks were immobilized, even small vehicles and motorcycles failed. The Germans improvised desperately. They built fires under engines to warm the oil, a process that took hours and created smoke that drew Soviet artillery fire. They drained oil at night, took it inside heated shelters, and poured it back warm in the morning. But this only worked if you had shelter and fuel for heating. They mixed gasoline with engine oil to thin it, which allowed starting but destroyed engines through inadequate lubrication. General-Lieutenant Gotthard Heinrichi, commanding 43rd Army Corps, reported on December 10, 1941, mechanical failures from cold now exceed combat losses by approximately 3 to 1. We have tanks with full ammunition and fuel but cannot move them. The infantry advances and the armor sits frozen. This is untenable. Meanwhile, Soviet forces operating in the same temperatures maintained significantly higher mechanical readiness. Their T-31s, KV-1s, and trucks continued operating in cold that paralyzed German equipment. Why? The popular narrative says Soviet equipment worked because it was crude, simple, designed for Russian winters. There's some truth to that. Soviet engineers did design with extreme cold in mind. But the real answer is more complex and more interesting. Soviet tanks used several cold weather advantages. First, diesel engines. The T-34 and KV series used diesel, not gasoline. Diesel engines have no spark plugs or distributors to fail in moisture and cold. They run on compression ignition, which is simpler and more reliable in extreme conditions. Second, better cold start systems. Soviet tanks had compressed air starting systems as standard equipment. Instead of relying on weak batteries to spin a cold engine, tankers could use stored compressed air to crank the engine with substantial force. This system was specifically designed for Arctic conditions. Third, simpler oil systems. Soviet engines had fewer tight tolerances and clearances. They were designed to run with thicker oil. A T-34 engine would operate, albeit roughly, with oil that would starve a German engine's tighter bearings. But here's the crucial point that often gets overlooked. Soviet oil quality was inconsistent. While Soviet engineers designed equipment for cold, Soviet petroleum industry couldn't always provide ideal lubricants. The Soviet Union had massive oil production, primarily from Baku and other fields, but refining technology was less advanced than American or even German capabilities. Soviet motor oils worked, but they weren't optimal. In extreme cold, Soviet vehicles had problems too, just not as severe as German equipment. This is where American involvement becomes critical. In 1941, the United States had the most advanced petroleum industry in the world, not because American engineers were smarter, but because American conditions had forced innovation. Consider the U.S. automobile industry had exploded in the 1920s and 1930s. Americans drove cars in Montana winters and Arizona summers. Truckers hauled freight across the Dakotas in January and through Death Valley in July. This created demand for lubricants that worked across extreme temperature ranges. American oil companies, Mobil, Standard Oil, Texaco, others, invested heavily in research. They developed better refining processes, additive packages, and multi-grade formulations. By 1940, American motor oils were significantly superior to European equivalents in terms of temperature performance. The SAE had established viscosity grades in the 1920s, creating standards like SAE 10W, SAE 20W, SAE 30. The W stood for winter grade, oils formulated specifically for cold weather use. By the late 1930s, American companies were producing oils like SAE 10W that remained pourable at temperatures that would freeze European oils solid. More importantly, American industry had scaled up production of these specialized oils. When the Lend-Lease program began in 1941, the U.S. could supply not just petroleum products, but specifically engineered lubricants designed for extreme conditions. President Roosevelt signed the Lend-Lease Act in March 1941. By June, when Germany invaded the Soviet Union, the supply pipeline was just beginning. But as Soviet forces reeled back from the German advance in summer and fall of 1941, American shipments ramped up dramatically. Lend-Lease wasn't just tanks and planes. It included 2,670,000 tons of petroleum products over the course of the war. This included motor oil, aviation oil, grease, and specialty lubricants, much of it specifically cold weather formulations. The first major shipments arrived in Murmansk and Archangels in fall 1941, right before the winter crisis. Let me give you a specific comparison, because abstract numbers don't tell the story. German Standard Military Oil in 1941 was essentially SAE 30 weight, suitable for moderate temperatures. At minus 40 degrees Fahrenheit, this oil had a viscosity roughly 40 times higher than at operating temperature. It was nearly solid. American SAE 10W oil at the same minus 40 degrees Fahrenheit had viscosity only about 8 to 10 times its operating temperature value. Still thick, but still pourable. More critically, it could flow through engine passages. Soviet equipment using American-supplied oil could start and run in temperatures that left German equipment immobilized. Lieutenant Dmitry Loza, commanding a Soviet tank company equipped with Lend-Lease Sherman tanks in 1944, later wrote, "The American tanks came with their own oil and maintenance supplies. The oil was remarkable, thin, even in severe cold. We could start our Shermans at minus 35 degrees Celsius, minus 31 degrees Fahrenheit, without external heating. Our mechanics who worked on both Soviet and American equipment told me the American lubricants were noticeably superior." But it wasn't just Lend-Lease equipment using American oil. Soviet logistics officers requested lubricants specifically, and American supplies supplemented Soviet production throughout the war. A Soviet logistics report from January 1942, now in Russian military archives, notes, "Receipt of 450 tons American motor oil, winter grade, distributed to tank units 2nd Guards Army, reported significant improvement in cold start reliability and reduction in mechanical failures." The German intelligence service noticed. A captured German intelligence assessment from February 1942 states, "Soviet equipment reliability in winter conditions appears to have improved from previous year. Interrogation of prisoners suggests American supplies, including lubricants, may be a factor. Soviet tanks are observed operating in temperatures below minus 30 degrees Celsius with fewer apparent difficulties than our forces experience." Let me explain what made American oil better, because the chemistry matters. Motor oil isn't just refined crude petroleum. By the 1940s, it was an engineered product with additives. Pour point depressants. These are chemical compounds that prevent wax crystals from forming as oil cools. Crude oil contains paraffin waxes that solidify in cold. Pour point depressants keep them dispersed as microscopic particles instead of letting them form a solid mass. Viscosity index improvers. These additives help oil maintain more consistent viscosity across temperature changes. They're long-chain polymers that coil up when cold and expand when hot, partially counteracting oil's natural tendency to thicken in cold. Detergents and dispersants. These keep combustion byproducts suspended in oil instead of forming sludge. In extreme cold, sludge formation accelerates.
detergents combat this. American oil companies were leaders in additive technology. Shell developed pour-point depressants in the 1930s. Standard Oil, which became Esso, then Exxon, pioneered viscosity index improvers. German oil companies had some additive technology, but their cold weather formulations weren't as advanced. Partly this was because they'd never needed oils for -40 degrees Fahrenheit conditions. German winters rarely approached that. Partly it was because German petroleum industry focused on synthetic fuel production, making gasoline from coal, rather than lubricant research. Soviet petroleum industry had the opposite problem. They had plenty of crude oil, but less sophisticated refining and additive technology. Soviet oils worked, but optimal performance required additives the Soviet chemical industry couldn't produce at scale. American Lend-Lease filled this gap.
December 1941 through February 1942 was the critical period where oil quality directly impacted military operations. The Soviet counteroffensive that began December 5, 1941, succeeded partly because Soviet forces could move, while German forces couldn't. Yes, Soviet tactics and German overextension mattered, but so did mechanical readiness. General Georgy Zhukov's forces attacking from the north had tank units that maintained 60–70% operational readiness despite temperatures below -30 degrees Fahrenheit. German panzer divisions facing them reported readiness rates below 40%, with cold damage as the primary cause. This wasn't just tanks. Trucks were equally critical. The German Wehrmacht depended on trucks for logistics, moving ammunition, fuel, food to frontline units. When temperatures dropped, German trucks, using inadequate oil, failed in huge numbers. Soviet trucks, many of them American-made Studebakers and Dodges arriving via Lend-Lease, all using American cold weather oil, kept running. Soviet logistics, supplemented by American vehicles and lubricants, functioned while German logistics froze. A German logistics officer, Hauptmann Otto Renz, wrote in January 1942, "We have supplies 60 kilometers back, but cannot move them forward. Half our trucks won't start. Those that do start break down within kilometers as thick oil destroys bearings. Meanwhile, Soviet trucks move on roads we thought impassable. Their vehicles seem immune to cold that kills ours." The arithmetic of winter warfare became simple. If you can move and your enemy can't, you win. Movement meant working engines. Working engines meant proper oil.
The oil story extended beyond Soviet-German combat. American forces in Alaska and the Aleutian Islands faced similarly extreme cold. U.S. military specifications for Arctic operations called for SAE 10W oil as standard, with even lighter SAE 5W for extreme conditions. American vehicles operated reliably in Alaskan winters that matched Russian severity. When U.S. forces fought in the Ardennes during the Battle of the Bulge, December 1944, they faced the coldest European winter in decades. Temperatures dropped to -10 degrees Fahrenheit, occasionally lower. American vehicles, using proper cold weather oils, maintained readiness. German forces, by late 1944, critically short of everything, including quality lubricants, suffered mechanical failures that compounded their defeat. British forces in Italy during winter 1943–44 faced cold, though not Russian-level extreme, and specifically requested American lubricants through Lend-Lease arrangements. British petroleum industry could produce adequate oils, but American supplies were preferred for reliability.
Quantifying oil's impact is difficult because military records rarely specify fail due to inadequate lubrication as a separate category. But we have some data. German data. Panzer divisions on the Eastern Front, winter 1941–1942, reported average mechanical readiness of 35 to 45% during coldest periods, December to February. Wartime strength reports specifically cite cold damage as primary cause. By comparison, summer 1941 readiness averaged 65 to 75%. Soviet data. Tank armies using Lend-Lease lubricants, documented in logistics records, reported readiness rates 10 to 15% higher than units using only Soviet oil during winter 1942–1943. Lend-Lease lubricant shipments to USSR. 1941, about 50,000 tons. 1942, about 220,000 tons. 1943, about 430,000 tons. 1944, about 680,000 tons. 1945, about 380,000 tons. Total, over 1.7 million tons of petroleum products, including motor oil, aviation oil, and greases. This doesn't sound like much compared to tanks or planes, but consider,
An average tank used about 5 gallons of engine oil per 1,000 miles. A truck used 3 to 4 gallons. The Soviet military operated millions of vehicles. Lubricants were consumed constantly and absolutely essential.
German forces weren't ignorant of the oil problem. They tried to adapt. By winter 1942-1943, German military specifications included cold weather oils. German petroleum industry, both domestic and conquered refineries in Romania, produced Arctic-grade lubricants. But quality was inconsistent and quantity insufficient. As the war turned against Germany, petroleum shortages became critical. By 1944, Germany was desperately short of crude oil. What they had went primarily to fuel: gasoline for vehicles, diesel for U-boats, aviation fuel for the Luftwaffe. Lubricant production was secondary priority. German mechanics began extending oil change intervals far beyond recommendations, using whatever oil was available regardless of specifications, and jerry-rigging field solutions that worked short-term but damaged engines long-term. A German tank mechanic, Feldwebel Ernst Hoffmann, captured in 1945, told interrogators, "By 1944, we used whatever oil we could find. Sometimes Soviet oil from captured stocks, sometimes aviation oil meant for aircraft engines, used in tanks because nothing else was available, sometimes oil drained from destroyed vehicles and refiltered. Equipment didn't last, but without any oil, it didn't run at all." Meanwhile, Soviet forces backed by American Lend-Lease had adequate supplies of appropriate lubricants. Not unlimited, Soviet logistics were always strained, but adequate, enough to keep equipment running.
After World War II, military specifications for cold weather lubricants became standard worldwide. The lessons learned from 1941 to 45 shaped military petroleum engineering for decades. The U.S. military developed the MIL-L specifications, MIL-L 2104 for combat vehicles, MIL-L 46167 for Arctic conditions. These specs required oils to flow at temperatures as low as -65 degrees Fahrenheit and maintain lubrication up to 450 degrees Fahrenheit. NATO standardization agreements ensured all member nations used compatible cold weather lubricants. The Soviet Union developed their own Arctic specifications, though they continued importing additive technology from the West when possible. Commercial applications benefited too. Multi-grade oils, 10W30, 10W40, 5W30, became standard in the 1950s to 60s. Modern synthetic oils can flow at -75 degrees Fahrenheit and beyond. The technology that started with military necessity became universal. Today, you can start your car in Minnesota winter or Montana blizzard because petroleum engineers learned, partly from World War II experience, how to make oil that works in extreme cold.
Here's what we need to acknowledge. American cold weather oil didn't save the Soviet Union. That's an exaggeration. The Soviets would have fought and likely won regardless, because Soviet industrial production was massive and growing. Soviet willingness to absorb casualties exceeded German capacity to inflict them. German strategic mistakes, invading in the first place, underestimating Soviet resilience, were fatal regardless of lubricants. Soviet design philosophy, simpler, more robust equipment, was inherently better suited to Eastern Front conditions. What American oil did was make Soviet operations more efficient and less costly. It improved mechanical readiness rates, it reduced maintenance burden, it allowed Soviet logistics to function more smoothly. In military operations, efficiency matters enormously. If one side's trucks work 70% of the time and the others work 50% of the time, the first side can sustain operations the second cannot. If one side's tanks are operational 60% of the time versus 40%, that's a meaningful advantage. American cold weather oil was one component of Lend-Lease, which was one component of Allied victory. Not decisive by itself, but significant in aggregate.
If there's a takeaway, it's this. Wars are won by logistics and engineering as much as by combat. The side that can keep equipment running, that can solve mundane problems like cold weather lubrication, gains cumulative advantages that matter over years of conflict. Germany lost the Eastern Front for many reasons: strategic overreach, inadequate logistics, Soviet resistance, industrial capacity imbalances, but among those many factors was something as simple as motor oil. American petroleum engineering, developed through decades of civilian experience in harsh climates, provided allies with a small but real advantage: engines that started when enemy engines wouldn't, vehicles that ran when enemy vehicles froze.
Next time you change your car's oil and see 5W30 on the bottle, remember, that specification exists partly because soldiers learned in Russian winter that oil quality matters, that temperature performance isn't optional, that something as mundane as lubricant can influence the fate of armies and nations. German tanks froze at -40 degrees Fahrenheit because their oil turned to sludge. Soviet tanks ran because, among other factors, they had access to oil that kept flowing. That's not heroic, it's not dramatic, it's engineering. And sometimes, engineering wins wars.